thank you to QCware for inviting me to give a talk here. So I will talk to you about some of the high-level research that we're doing at Goldman Sachs in quantum computing. I'll begin with some of that and a bit of our philosophy. And then I'm, in the middle, going to kind of dive a little bit deep into a recent technical result that we have. And I think it might surprise some of you. It's going to be a very negative result. And it's going to tell you what you shouldn't do with a quantum computer. But I think that goes a bit to our philosophy, which is we really want to understand what quantum will be good for ourselves and for our clients, and what it won't be good for, so that we don't try and oversell this. Okay, so let me just tell you a little bit about typically how we work. We tend to work backwards. And what I mean by that is we take algorithms, typically that are known, that might potentially provide an advantage for a financial use case. And in detail, we will work through these algorithms to figure out exactly how large of a computer, how big of a circuit, how fast of a quantum computer in terms of clock rate, things like that we will need to achieve advantage. And how do we define advantage? I think it was spoken in one of the earlier talks. Typically, speed is what really matters in a financial setting, which is hard, right? Quantum computers are not really high throughput machines or low latency, right? They typically, you think of Shor's, it's like take something that will be lifetime of the universe and bring it down to months or whatever type solution times. Here, right, we're often like we want things from seconds to milliseconds, things like that, which is hard for quantum computers. The positives, right, if we can provide advantage, right, financial applications, often there's a very close connection between an algorithmic advantage and an actual useful value, right? And so that's a positive. But as you'll see here, many financial applications are not obviously quantum native, and I'll get into a little bit of that. So some of the things that our team does, I've mentioned resource estimation. I think this is the bulk of a lot of what we do in order to define whether or not we'll have advantage, and that's what I'll talk about in some of the technical results that I'll share with you. We also do algorithm design. So let's try and come up with new algorithms that might improve things. And then finally, hardware integration, and that includes both error correction and specialized hardware, and I'll talk a little bit about that today. Most of what you'll see from us is we're looking far into the future with fully fault-tolerant quantum computers, not necessarily NIST, not that we're not interested, but just most of the stuff that you'll see from us assumes a fault-tolerant quantum computer. And so that suggests that with our algorithms, we do need to consider the underlying quantum architecture, including all the quantum error correction and stuff that's going to be involved with that. We collaborate a lot with both industry, startups, and academics. And in fact, the stuff that I'll share with you today was a very nice collaboration with AWS. Okay, so where are we today? This is the plot that we often like to share to kind of put in perspective where the current state of quantum computers are, and then the algorithms that we have developed and are looking at and kind of where they lie in this. So right on the x-axis, it's just number of qubits, and then the program depth, sort of the amount of time it takes to run an algorithm on the y-axis. And those dashed lines are then the error rates that you might need to execute an algorithm of that size. All right, and it's basically, if you look at it, it's the width times depth, 1 over that, right? That's roughly the error rate that you're going to need, right? And so the bigger the circuit gets, the lower the error rate you're going to need. We know that the HPC horizon, like where classical can simulate to, is roughly around 50-ish qubits, somewhere around there, right? If you have noisy systems, you can probably simulate out a bit further for shallow depth circuits. The NIST scale, right, lies somewhere maybe here. These are kind of just large boxes drawn on a plot, so don't quibble too much with exactly where the boundaries are, but right somewhere in the 100 to 1,000-ish qubits regime. Breaking RSA, right, these really well-known use cases for quantum computer, they lie in the upper right-hand corner. And then, of course, QPUs today tend to live down in this lower left corner. So obviously, everyone keeps trying to push up and to the right, but we're not there yet, right? Thankfully, improvements are being made, right? IBM announced, I think, last year the Eagle QPU, and now there was even a more recent one, I think just a week or so ago that didn't make my slide, that continues to push further out to the right, which is great. Obviously, we also want to go upwards as well in terms of program depth, but that does require the lower error rates, as I mentioned. Just highlighting a few of the algorithms that have been published, and I've got the references down there if you'd like to read more about them. Derivative pricing, and so what these dots here are showing is what we estimate where useful advantage will happen. In other words, where might a quantum algorithm meet or exceed current existing classical approaches, right? Because that's how we define quantum advantage. And here, these are typically time to solution. Can we beat the current classical? And it might surprise you that these are quadratic algorithms. These are algorithms with just a quadratic improvement, but in fact, it looks like you could obtain a useful advantage. So there was derivative pricing, and then more recently, there was some work on estimating what are called the Greeks. For those in the financial world, you'll know what these means, but essentially they're like derivatives of contracts. So and they help you with hedging and things like that. Qubit count error rates, of course, matter, right? We can estimate kind of, and you'll notice here on these error rates with these things that are plotted, right? They're somewhere in the 10 to the minus 9, 11-ish regime, right? That will require a fault-tolerant quantum computer, right? For these algorithms as we've estimated them. But also clock speed matters, right? Time to solution is important to us. And so somewhere we've estimated that these require somewhere around a 7 to 50-ish megahertz logical clock speed. And I think that's something that, as we also work with the hardware partners to understand, can the quantum computers that are being developed today, will they be able to achieve these logical clock speeds? And of course, there's a whole bunch of work that goes into working through that. Okay, so now with that landscape, I now want to talk about some new results that we just put out on the archive right before Thanksgiving, and this is on portfolio optimization. And as I mentioned, I'm going to spoil it, it's a negative result. But I think it's important for us to be able to share these results and to share kind of the level of detail that we went into to really truly understand this. The positive from this is that we really understand this well, and I think it provides us a roadmap for what we need to improve in order to make these things useful. Okay, ignore the math if you're not a math person, but this is just a textbook portfolio optimization problem, okay? And so what is portfolio optimization? I have a bunch of stocks that I want to, or a bunch of money, and I want to allocate it to a bunch of stocks. How do I maximize return with the minimum risk? Okay, pretty straightforward. That's it. You might have some constraints in there. Maybe your budget's limited. You don't want to. There's some maximum transaction size, things like that. Perhaps no short positions. You can change. There's a lot of different variants of this. This is just a standard textbook example. Okay. The nice thing is this is a convex problem. And so there are many classical solvers that exist out there today that can solve this problem very efficiently. So why would we look at such a problem that a classical computer can solve today? Again, but it's a very important problem, one that's widely used. And nicely, there is a quantum algorithm that has been proposed for this, the citation down there, for portfolio optimization. And in particular, it was for exactly this problem, this convex problem. And it essentially quantized an algorithm called the interior point method algorithm, and it solves these types of convex optimization problems. And what they showed was that it looked like there was at least a polynomial advantage. There was some sort of speed up, classical to quantum. So our question was, okay, this is an important problem. There's this polynomial speed up. How big of a computer are we going to need to achieve advantage? Some of the technical details that I'll go into is that as the way this algorithm works is it's essentially an iterative algorithm. It starts at some beginning portfolio, and then it'll iterate, just keep adjusting the weights until it finds the optimal portfolio, and it follows this mathematical prescription, as I mentioned, called this interior point method. The compute step that's hard in that process is that at each step of the iteration, you solve a linear system, right? Ax equals b, you solve for x, where A is some matrix. And these are vectors, right? Well-known linear algebra problem. Many classical techniques to solve linear systems exist. But of course, there's a quantum algorithm that in some cases can achieve exponential speed up. So what was shown in this paper is that if you swap out the classical linear system algorithm for a quantum linear system algorithm, this portfolio optimization can achieve this polynomial speed up. Now, what you need to do this is you have to do what's called a block encoding of A, this matrix that you need to invert, and I'll tell you what that means in a minute. You need to prepare a quantum state, and I think we've seen that in some of the previous talks, discussions on that. And you have to be able to then read out the solution state. Many of you are well aware, so a block encoding is essentially just load classical data into my quantum computer. Just think of it that way. Okay, block encoding is in a particular form, but just There's nothing else you take away from that. It's basically, how do I read in classical data into my quantum computer? Okay? Read out the state's the opposite. I have quantum data and I need to read it out to get classical information from there. Turns out these are real bottlenecks. And it's not surprising. We kind of knew this, but these algorithms require it. So what we actually did is this kind of led us on a segue to look at just this pure problem of block encoding a matrix of classical data. Okay, and again, this is, I mentioned at the start, financial use cases are often not quantum native, and I think this is a really prime example. Quantum computers can do unitary operations, which are very special forms of matrices. Financial data is often not arranged in such a nice way. It's just arbitrary data. You can take any amount of just classical data and put it into a quantum native unitary through this thing called this block encoding, where you basically just stick it up in a block of a unitary, and everything else is something sort of arbitrary just to fill it out. The nice part is it's been shown over the last 3 or 4 years is that basically all quantum algorithms can be cast into this form, and there's many very efficient forms of quantum algorithms that use this language of block encodings. Okay? Linear systems, Hamiltonian simulation, all of the things that you've probably heard about with quantum chemistry, things like that, they're often now being written in this language. And so this is a very useful thing to understand. You know, how much does it cost to load classical data into a block encoded form? As I said, it's sort of the underpinnings of almost all quantum algorithms to date. So we worked through this, and I'm not going to go into the details of this, just to say that there's a paper out on the archive now, actually happily just accepted, that goes into all of the details, and this is again with our partners from Amazon, of what it takes to block encode a matrix. And again, you know, down to both parameterized forms of the resource estimates in terms of qubits, TDEPs, T-count, these are all resources, number of qubits, for a whole variety of different ways that you can do it. You might, you know, different types of QRAM. I think there was questions about QRAM. You need to, you know, how you load the data, how you prepare states, things like that. But at the end of the day, we can get out the resources. And so the nice thing is not only now for our portfolio optimization problem, but now really any algorithm that requires this as an input model, of which there are many, we can just say, not useful, it's going to take this many resources to load our data, forget it. Or this is potentially useful because yes, we know we can just basically go to our tables and our estimators to understand how big of a computer this is going to take. Now, jumping forward to the portfolio optimization problem, this chart here that I'm not, again, going to go into detail is just think of this, if any of you have done code profiling, written code, have done a code profile, this is a code profile. It breaks down the quantum algorithm into all the various subroutines that are needed to solve this portfolio optimization problem as it was spelled out, okay? You can't really see the numbers here, but you're going to, maybe down here, but you can certainly see these. Those are astronomical, okay? And that's why I say this is a negative result. So no way this will ever be practically useful. You could get your best possible gate speeds you could ever imagine, and this thing will take, you know, millennia to solve, despite using what we know to be the most optimal linear system algorithm and this portfolio optimization. And I think this, to me, highlights the utility of really going deeply, you know, down into these algorithms that are, you know, developed. Asymptotics matter, sure. But when it comes to like achieving real, true, practical advantage, you really have to go to this level of detail to understand how big of a computer am I going to need. And I'm going to point out that this is for a portfolio of 100 assets. Classically, we can solve that in seconds. It's trivial. This is not even really an interesting problem. So I think this just highlights to me, you know, again, that we want to be very careful about. You know, lots of papers, lots of hype, lots of things going on. And we are, I think, as excited as anyone about quantum, and we believe there are true advantages in finance, but we have to be careful about some, you know, sometimes it's just, you know, something that may not be important. But the other thing to point out is perhaps someone can take this, right, researchers in the field, and we really point out where the bottlenecks are. So hopefully this spurs people to try and reduce these bottlenecks. So maybe at some point, and there's a lot of orders of magnitude we need to bring this down, but perhaps it might be possible. Okay, so just I'm going to conclude with my last minute here, just saying, okay, we had this landscape of quantum power. Where do these things sit? These are now where these results sit. And this is a little bit of a cluttered chart, but I mentioned this block encoding. This is how we load classical data into the system. We had a whole variety of ways you can do it. Many algorithms that exist today, and what you'll see quoted is, oh, I'm going to load my classical data, and there's a log depth block encoding. That means sort of exponentially suppressed or exponentially short, which is nice because it provides all these nice asymptotic speedups. The problem is if you're going to load classical data with that shallow of a circuit, it actually requires a very large quantum computer. The number of qubits basically is the same size as the number of classical bits, which is not exactly what you want. Now you can trade that. You can start reducing the number of quantum bits you need. The expense is that you ultimately have to use a longer program depth. And I think it was pointed out that in the limit, it would be exponential depth if you want a very small quantum computer. And also, I'll just point out, this really highlights the problem of quantum algorithms that assume you have access to a lot of classical data. These are encoding matrices of 16 by 16. That's what these numbers are, 256 by 256, 40, and the numbers are getting cut off here, 4096 by 4096. Not large matrices by any stretch of the imagination for a classical computer, right? We deal with things of these size all the time, right? I mean, these are small, but it actually requires, right? These are the two dots for our derivative pricing papers. Just encoding a 256 by 256 matrix is already a quantum computer of size larger than these. The beauty of these is that the data in was very small to specify the problem. And then finally, I just stuck a dot on as far on the upper top as I could for the portfolio optimization, because and there's the citation to that. A lot of detail in that paper if you want to take a look. Okay, a couple of key takeaways, and I know I'm basically out of time here, right? Block encoding, loading classical data is expensive, and this is not, I think, certainly to experts in the room, not a surprise. We've known this forever, but a lot of papers say, oh, you just block encode data and you're good. No, it takes a lot of resources to do that, especially classical data. The other thing, I think a key takeaway is quantum linear systems algorithm is often pointed out as a key subroutine in many things. The constant factors are still very, very large. I think it is going to be a useful algorithm, but there's still work that needs to be done to make this useful for our types of use cases. Hidden in there, we looked at portfolio optimization, but really, again, the quantum piece was a linear system. And right now, even a 100 by 100 linear system on a quantum computer, dense linear system of classical data is probably unrealistic for a quantum computer to do. Classical computers, right, can do that very, very, very easily. And then finally, actually, I didn't mention this too much, but underpinning all of this was then the readout problem. How do I read out the quantum data? That's a very large overhead as well. And so something, again, you probably don't want to do. There's some research directions I think that this could lead to, right? Really, can I get rid of this needing to read out data? But there's some real technical challenges there that make this hard. I'd be happy to talk to folks after this if you want to hear more about this. Again, there was a question on QRAM earlier. We really do believe that if we are going to load classical data, you probably want to do some optimized architectures. We can share all of our circuits are in there on how you do this. So then the question is perhaps there optimized architectures and hardware to do this, right? Classical computers don't use the same hardware for RAM and as CPU memory, cache memory, things like that. I think quantum computers in the future probably will be the same. And then finally, improvements to linear systems. Okay, I'll just leave this up here as my conclusions. We're always looking for partners and collaborators, improvements to relevant algorithms, especially super quadratic. We've talked about some of the quadratic algorithms, polynomial speed, but it'd be really nice, I think it was said before, to get some exponential ones in there. Also, error correction, right? That is actually something we're also interested in because we are typically looking longer out to fault-tolerant algorithms. All the resource estimates I showed you here today were done essentially by hand with some Python code to kind of help us along the way. We work with some tools as well. We have, but we're also looking there as well. And then here's just a summary of some of the other papers that I haven't really talked about today. Thank you.
Thank you, Dave, for a great talk. We have time for just a couple of questions. So this gentleman here.
Hello, my name is Dikshant, research scientist at SobServe. I really wanted to ask you a question about the research philosophy that Goldman Sachs has, which is essentially working backwards from concrete problems rather than going from bottom to top. And I also talked with Nikitas over the summer in Tokyo, and I wanted you to sort of like elaborate on this philosophy rather than taking specific use cases and building upwards. using the near-term devices that we have today, but instead of that, working backwards and what are the possible implications of this? Where are we headed towards if we use this approach? Thank you very much.
Yeah, that's a great question. I think, first off, I think we do both, but we tend to favor this backwards, concrete use cases. And I think really our philosophy is that that's truly, that's how we can create value, right, in some sense, is we have concrete problems. We know if we can beat how we're currently doing it today, that we can actually add value, right, to our customers and our clients. And I think that sort of underpins our philosophy and why we do that working backwards. I think to some extent it's very easy to just generate algorithms to try different things. It's a much harder thing to prove that they're actually going to provide useful speed-ups for really practical use cases. And I think that's why there's tons of papers just constantly coming out about various quantum algorithms for this, quantum algorithm for this. But I think as this portfolio optimization problem showed, this was an algorithm with a polynomial speed-up over classical algorithms. But once you really get into the details and work backwards to figure out what problem size is it useful for, is when you find out maybe not, right? And I think that's why it helps us cut through the hype, kind of doing a lot of this resource estimate going backwards. But with that said, we also certainly are interested, I think, in the reverse problem of, as you say, coming up with algorithms and as well. It's just a little less of a focus at the moment.
Thank you for the very illuminating presentation. I wanted to ask about the weights. Were you looking at discrete variables or continuous variables when you were doing the resource estimation?
These were continuous. Yeah.
Okay.
Essentially. I mean, discretized at some level just by floating point accuracy and things like that, but continuous.
Okay, thank you.
Any other questions? Oh, one over here.
Which I should point out, of course, is an approximation, right? You typically buy in discrete chunks, but yep.
Yeah, thank you for your talk. Did you also look at annealing, or is your direction only for gate quantum computing? And then the second question is, you showed adiabatic evolution, so is that similar to like QAOA, which isn't, I don't think that has a proven speed up.
Yeah, that's actually a great question and a great insight. I kind of sped through that slide due to time. Let me actually answer the first question first. We typically look at just gate-based algorithms. I don't think that's to say that there's not something interesting else out there. It's not an indictment of anything. It's just that's what we look at. I think to answer your first question. That particular algorithm for linear systems is a recent result from the academic world as the provable optimal asymptotic algorithm for quantum linear systems. And it just so happens that they used ideas from adiabatic quantum computing for the proof. They used these block encoding ideas to do it. So yeah, it's not to be confused. It's a fully gate-based algorithm. It just happened to use ideas from adiabatic quantum computing in the proof. And so that's why we said, and there's sort of two steps. There was this adiabatic step followed by what's called this eigenstate filtering thing, where basically if you think of adiabatic algorithms, you want to stay in the ground state. What they showed was that you can allow yourself to go quicker, you kind of escape, then you filter it at the end to just get the ground state. So it has ideas from that, but it is very much a gate-based quantum algorithm.